solve for the second derivative of theta. Specifically, what you would end up getting is 1 over 2 I d2 theta dt2 plus, that should be 4 right there, plus 1 over 2 k d squared theta equals 0, where I have canceled a couple factors of 2 that appeared on both sides of the equation. I've also canceled a common factor of my velocity. So I see a couple questions in chat. Is x the distance from the center of the mass to the spring? X is the distance that your spring is going to stretch. So this distance would be x. So if I draw an exaggerated diagram, let's see, we have some distance d. There's going to be that angle. This is going to be angle theta. And then this thing is going to be x. Whenever we have small angle approximations, this just means thing. I want you to go back. Thank you. This just means that x is equal to d theta. So this is what the small angle approximation means. This is where you're able to use your arc length functions. So in this specific problem, d is equal to r over 2. I haven't incorporated r over 2 because I want to use the result for the first multiple choice question. And if one notes that the moment of inertia of a disk is equal to 1 over 2 mr squared, that's going to give you a differential equation that looks like equals negative 2 kd squared over mr squared times theta, which implies that omega is equal to 1 over 2 pi square root 2k over m d over r, which means that the period is equal to 2 pi over omega. There we go. So whenever you have a simple harmonic motion, your final expression needs to look something of this form. Your expression needs to look something like this, where you have a second derivative is equal to a minus sign times a constant times the original function, where this thing that we have here is the square of our angular frequency. Omega squared is equal to 2k d squared over mr squared. So then I see a question in chat. When differentiating, wouldn't the chain rule apply in this situation? Yes, it would. Though I skipped a couple steps. Here, basically, when you differentiate, you have a common factor of the derivative of theta. So you basically end up with the derivative of theta with respect to time in the first term, derivative of theta with respect to time in the second term, and they end up canceling. Will the question on your final be of similar difficulty to this question? I would say Like, I never want to say harder, but then I also don't want to say easier because different people find it at similar levels, at different levels of difficulty. So what I'll say is it would be a little on the hard side, though I would say if you can do the questions in the lecture where we have simple harmonic motion and get to your differential equation, and you can do the final exam question that I'll be going over today, then I think that'll set you up nicely for the final exam. So the way that I'd approach these questions is we have two approaches, energies and forces. Sometimes in principle, both approaches will give the same answer, but one approach may be considerably easier than the other. By this, I mean, there are a bunch of parameters in the problem. Do whichever approach is easiest to deal with every parameter present in the problem. Instead of the second derivative, can you just write alpha? I'd write the second derivative. The reason why I do that is because that's standard notation across physics, where whenever we write simple harmonic motion, it's always explicitly second derivative of some angle with respect to time. So another question is, why is there a 1 over 2 pi? The reason why it's 1 over 2 pi is because we're considering angular frequency. Specifically, we have this relationship. We have, and then this is why I have the next slide. We have the period of some function is equal to 1 over the frequency. And we can relate the angular frequency to be equal to 2 pi times the frequency. So that means that if I solve for frequency, that gets me an... Oh, I see what you're saying. I see what you're saying. Sorry about that. Yeah, this 2 pi is wrong. Much better. Thought you were talking about the other 2 pi, but yeah. Sorry about that. And here I wrote it down in my notes. Always fun to make mistakes in notes, not realize it. So the last thing that I want to end off with is in this problem, we have d is equal to r over 2, which means that when you substitute things into the period, that becomes 2 pi. Yeah, 2 pi square root 2m over k. Basically, we have a square root 2 on the bottom, and then we have a 2 on the top, so we end up with just multiplying by a square root 2. Anything I can clarify about this problem before we go on? Will this session be recorded? No, it won't, because we're going through the final exam problems, and I've been told not to record the session. Yeah, so will we have a break in between? Yeah, we'll probably have a break just because 4.5 hours is a really long time. Can we go through the multiple choice? Yes, that's the next plan that I'm going to do. And then can I rewrite the third line? It's a little hard to read. Yes, I can. I d theta dt d2 theta dt2 plus half k d squared theta d theta dt equals 0. There we go. So then what I want to do now is to focus on the multiple choice questions. There we go. And I apologize for the small typing. I wanted to put everything on a single slide. So what we got was the period is equal to 2 pi square root 2m over k r over d. And then that means, let me call this T1. And then if I call this T2, where we decrease the right end of the spring and we decrease the distance between the right end of the spring and the center of mass by a factor of 10. So that means T2 is equal to 2 pi square root 2m over k r divided by d over 10. So that means that T1 over T2 will be equal to essentially, here I'll just write down the entire mathematics. R divided by D divided by 2 pi square root 2m over k r divided by d over 10, which is going to be equal to, let's make sure I do this properly because there's a lot of fractions, d divided by r over d over 10, which should be equal to, not 1 over 10. I believe it should just be equal. Yeah. That is equal to 10, 1 over 10, which means that T2 is equal to 10 T1, which means that the answer is going to be A, and I'll let Dida know about that. I don't think which T equation is wrong. You're right, that one's wrong, but in the end it didn't matter because we have squared m over 2k. Yeah, let me check that. Yeah, so the reason why I wrote it as D is because I wanted to, yeah, the reason why I wrote it with D is because I wanted to essentially write it in full generality. In the specific problem, we're given we have D is equal to R divided by 2. And then what the multiple choice question is asking is we decrease the distance by a factor of 10. So basically, D becomes R over 2 divided by 10, which is basically going to become just D over 10. All right. So the reason why RD is outside the square root was because when we derived the angular frequency formula, we got D over R is going to be we multiply some constant by d over r, where in this case we have d is equal to r divided by 2. Though in the first multiple choice problem, we're saying that we decrease the distance by a factor of 10. So this is why I kept it as d divided by r. Right, yes. So right. So the way that I got d divided by r was by keeping the location of the spring arbitrary. I know that it's somewhere on the disk, but I don't know where on the disk it's going to be. So then that's why I wrote it as d. So what I want to do is I really wanted to start the final exam problems at 2:30, and I'll keep to that schedule. So this means, what do I want to do? I want to focus on 2 multiple choice problems. So what I'm going to do is focus on the 2 multiple choice problems that I think is most relevant for the final. So this is basically how I approach the final exam, the help session. Basically, there are a number of questions that I received, and then due to a lack of time, I'm not able to go through all of them. But what I do is basically code the questions into what I think is going to be most appropriate for the final exam. So this is why on question 4, we're asked, we have some sort of spring undergoing simple harmonic motion in the horizontal direction, and we're going to add some sort of mass to the spring when the spring is at its maximum amplitude. So what that means is we have spring like that, there's going to be some sort of maximum amplitude, and we're going to increase this mass. So this mass is now, so the mass goes to like some capital M plus M. So the mass is going to increase. And we're asked what's going to happen to the kinetic energy of the mass. Basically, regardless of whether the mass increases or decreases, the kinetic energy is going to stay the same. The reason why it's going to stay the same is because at the maximum distance from equilibrium, we have the energy is just going to be half Ka squared. The amplitude is something that we basically set by hand. It is something that we're able to choose within the problem. The spring constant is something that comes with the problem itself. So the spring constant is a property of the spring. So the upshot of this is the total energy that we have to work with has no bearing on what the mass of our object is going to be. So the kinetic energy is going to fluctuate between 0 and some sort of maximum value at its equilibrium point. That means the speed is also going to fluctuate between 0 and some maximum value at the equilibrium point. When we change the mass, the speed is definitely going to change, but the kinetic energy itself is going to be constant. So then that's the main takeaway from this problem. Basically, if we change the mass right at the end of the oscillation where there's not going to be any kinetic energy present, that means that there's no way the mass can change what the maximum kinetic energy is going to be. So it has to stay the same. And then, since I have 2 minutes, what I want to go through is question number 5. The reason why I want to go through question number 5 is because I think it's a really nice way of looking at simple harmonic motion. So what we have is the equation for simple harmonic motion. X of t is equal to a cosine of omega t plus phi. This thing is called the phase angle. So basically what we're asking for is, what must this phase angle be when we have this situation? We have a mass is on a spring, and the distance from the mass to the equilibrium position is half of the amplitude. So basically this is where we note that x of t is equal to x naught over 2, which is equal to x naught cosine of, what I'm going to do is write just phase angle. And then essentially what I can do is get my phase angle to be the inverse cosine of 1 over 2. And then when I do that, and I note that I'm going to get 2 solutions to my phase angle because cosine is a multi-valued function. But then I would denote that we're moving towards equilibrium, meaning that the velocity has to be positive, and then that means that essentially my phase angle becomes 4 pi divided by 3. Now, I see a few questions in chat. So regarding terminology, you can blame physicists for this. What we call phase constant specifically refers to phi. What we call phase angle refers to omega t plus phi. And so then phase angle is something that the terminology is in the textbook. So we did talk about omega t plus phi, though the textbook specifically called it phase angle. So then to recap question 5, what we did was, whenever we have simple harmonic motion, we have x of t is this quantity, a cos omega t plus phi. And then what we need to do is to say x of t is equal to, thank you, negative 1 over 2 x naught. And then that's just equal to the amplitude times the phase angle, times the cosine of the phase angle. Then essentially we take the arc cosine of the phase angle and impose the condition that because we are moving towards the equilibrium point, the velocity has to be greater than 0. I see another question in chat. What happens if we change the mass at the equilibrium position? This is a very good question because at the equilibrium position, there's not going to be any energy coming from the spring. Basically, the spring is relaxed. The potential energy of the spring is going to be 0. All we have is the kinetic energy. EK is equal to half mv squared. But then if I add some mass to, I add some mass or I take away some mass to the system, basically what I'm doing is changing the, basically what I'm going to be doing is changing my velocity. I'm going to be changing my mass, and then that's going to affect the kinetic energy. So the way that you'd see this is by noting that you would use conservation of momentum. So essentially, initially we have mass times the initial velocity is equal to mass plus some added mass times the final velocity. And then if we know what my mass is, we know what our initial velocity is. This is something that we're given in the problem. And we know how much mass we added, then we know what our final velocity has to be. So then we know what our kinetic energy has to be. Right. So then, since I'm 3 minutes over time, I'll just write down for question 3, basically what you'd do it is cos of omega t1 is equal to 1 over 2 cos of omega t2 equals 1 over 2, where t2 equals t1 plus half. And then you can solve simultaneously for omega and time using properties of trigonometry, and you would get this answer. So is that the only way to change A, adding mass at equilibrium? For this purpose, yes, you basically have to do something to change the energy. Yeah. So then the reason why I didn't worry about the phase angle in 3 is because phi is going to be, the reason why I didn't need to worry about my phase constant in 3 is because phi is basically my initial condition. So I set phi equal to 0. I chose my initial conditions of the system to be, to correspond to phi equals 0. So this is something that you have freedom over. You're always able to basically, whenever you have a chance to choose your initial conditions, it's good to make it so that phi is equal to 0. Now, what I want to do for the next 4 hours, or possibly 3.5 hours with some break in the middle, is work on the long answer problems. Reason why I want to work on these long answer problems is because, in my opinion, on the final exam, I feel like the long answer problems will be harder than the multiple choice problems. That's partly because the long answer problems are worth approximately 15 marks each. And then also long answer problems have a fewer number of topics, meaning that, let's say that you completely blank on, I don't know, some very specific kinematic quantity. On the multiple choice, that might hurt you, but on the long response, that's not going to be horrendous. Not knowing something about rolling motion, however, that's going to be very bad. So what we have to do is we have this system where we have a mass attached by a spring on each side. And what we're going to do is to basically figure out what is the angular frequency of oscillation. So how would one approach this problem? Free body diagram. Right, so whenever you see forces, draw a free body diagram. You will never be led astray. Even if you don't ultimately use the free body diagram in your final solution, it's good to just have it just in case you realize that you're able to solve the problem easier using forces and torques. So basically you draw a free body diagram. Now, let's say that we displace the mass towards the right. If I displace the mass towards the right, what forces are going to be? Where are my forces going to point if I've displaced the mass towards the right? Correct. There would be two spring forces towards the left, K1, X1, K2, X2. The reason why there are going to be two spring forces is why. So more specifically, why do both spring forces point towards the left? Right, because they're both restorative. They both want to return to equilibrium. Your force for your spring always points towards the equilibrium point. So if we've displaced the mass towards the right, that means both forces have to point towards the left. So let me draw this situation. We have the mass, it has moved some distance towards the right. And that means that spring K1 has increased in length by a distance x1. How much has spring 2 compressed by? The same amount. So specifically, drew it in the wrong place. Well, this is why I'm not an artist. We'll do it like that. So then x2. Now, what we've identified is x1 is equal to x2. So that means that our object travels basically some distance x that's just equal to the distance that the spring compresses or the distance that the spring expands. Now, let me apply the free body diagram. What we know is the net force is equal to negative k x1, negative k1 x1 minus k2 x2. And then we also know that the net force is equal to mass times the acceleration. So that means that my second derivative of my position with respect to time is equal to negative k1 x1 minus k2 x2 over m. So then what is going to be my effective spring constant here? It's going to be k1 plus k2. Basically, we can rewrite this as negative k effective times x divided by m. So what the effective spring constant does is it lets you write all of your spring constants just in terms of, you can relate them all together so that you can define an effective spring constant. So that's what the effective spring constant does. It lets you treat multiple springs as a single spring, provided you have the right constant, the right spring constant. And then this is just going to be multiplied by the location of the mass. So basically, to determine your effective spring constant, what you want to do is write k1, k2. So you want to relate k1 and k2. And then you also want to relate x1 and x2. So then when you relate them, basically subbing in your equations will get you something that looks like this. So then I see a couple questions in the chat. Why is kx negative? Kx is negative because it points towards the left. If you prefer, this direction is negative, this direction is positive. Another way of thinking about it is kx is a restoring force. So it's always going to point towards equilibrium. Why is d2x by dt2 just f net over m? It's because the second derivative of x is an acceleration. So I just rewrote what a is. So another question, will this form always be true? So rewriting it, whenever you have a multiple string constants, so let's say you have k1, x1, k2, x2 plus dot 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 plus kn xn, what you're always able to do is rewrite this as some effective spring constant times the position. You're always able to do that. Similarly, if you had energies present, so you have half k1 x1 squared plus half k2 x2 squared plus dot 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 plus half kn xn squared. This thing is going to be always equal to half k effective x squared, where the form of k effective, the form of k effective and the form of x really depends upon what your specific situation is. So the way that you get k effective is you basically rewrite your simple harmonic motion equation in terms of x, and then whatever's multiplying x, if you're dealing with forces, is going to be k effective. So then k effective will be k1 plus k2. Can we assume that the equilibrium of the system is in the same location as the equilibrium? The equilibrium of both springs is in the same location as the equilibrium of the system. Yes, you can. If the system is in equilibrium, that means that the springs also have to be in equilibrium, meaning that they are automatically at their equilibrium length. So there's another question, why don't we set the acceleration negative? It's because when we displace the mass towards the right and we let it go, the mass is going to speed up as it approaches its equilibrium point before it begins slowing down again. So this is why the acceleration is positive. Is explicitly writing k effective necessary in your solutions? No. So what I mean by this is you can do the entire solution and maybe that you get that your angular frequency looks like k1 plus k2 over 2 minus k1 over 3 divided by n. Maybe you get something that looks like this. Well, you can always identify k1 plus k2 over 2 plus minus k1 over 3 as k effective, but you don't have to explicitly write it in your final answer for omega. You would either say omega is equal to the entire thing with all your k's present, or you could say omega is k effective square root of k effective divided by m, where then you say where k effective is equal to whatever. So then is it mandatory to define k effective? If you use k effective, define k effective. Since I know that when I was marking it, if I'm marking something and I just see k effective, but nowhere in the problem do you define what k effective is, I'll dock you some marks. I won't dock you that many if the problem is still right, and it does correspond to the right to k effective, but if it's not there, you'd probably get docked a mark or two. What if both springs are stretched initially? In this case, that won't be possible. The reason is because in this setup, if we stretch one spring, we automatically have to compress the other spring. There are ways in which we can cause multiple springs to compress, one spring to compress, one spring to expand, but that really depends upon the specific setup we're considering. Are Dita and I grading the final exams? No, it's going to be the TAs. Yeah. And then we basically told the TAs that we need the exams marked sometime next week. I remember when I was marking them, I was given 5 days to do it. So I ended up marking them on a layover in Chicago. I had a 9-hour layover. I needed to do something, so might as well mark EC 105 exams. Why is W equal? Hold on, wait. Oh, omega. Oh, so what I wrote down here, this was just an example. So this right here is illustrative example. Yeah. Sorry for the confusion about that. So essentially, we want to find the angular frequency of oscillations. Whenever we have a differential equation, we're going to get something of the form second derivative of some function is equal to negative c squared times the function. Here, whatever this is, omega is equal to c. Basically, whatever is out in front, whatever is the coefficient, you can identify that with omega. So then you'd be done this question. This one, I can't remember. I think this was a 12-mark question on the 2018 exam. There were multiple parts to it, but basically everything came down to getting the differential equation. Are there any other questions about this? Thank you. In one of the example problems, we end up with the differential equation that had an additional term and not depend on x. Right, yes. Do I have, what do I want? Do I want to use the space right there? So then the final answer, basically the final answer will be whatever is the angular frequency that you calculate right here. So before I answer that, what I'm doing is Dita also did this problem. So then what did she say is the final answer? Okay, I'll write down the same thing she wrote. So then the same thing she wrote was that omega would be equal to k1 plus k2 over m square root. Is this difficulty comparable to the question on the final? I say the final question will be on the more difficult side. Yeah, k1 plus k2. So then before I go on to the rolling motion question, what I'm going to do is talk about, we have d2x dt2 is equal to negative omega squared x plus, what was it? It was like m plus 1 over 2m, something like that. So if you get an equation that looks like this term is your angular frequency. This thing is basically related to your initial conditions. So the thing on the end, that's going to be relevant to solving the differential equation, but you're not expected to do that on the final exam. That would be a higher level classical mechanics course. So on the final exam, if you got this equation and you're asked what's the angular frequency, then you can just say, well, here's what the angular frequency is, or more specifically, if you got something like d2x dt2 equals negative omega squared x, you can write down that x is equal to a cosine omega t plus phi, and then omega is equal to whatever the answer is based upon your problem. Right, so then I'll add the last question here. The C was for illustrative purposes. So the C is just showing whatever constant you have out in front there, that would be omega. So let's go on to this problem where there's a desire to solve this parametrically. And in fact, I have exactly the same desire. I do not like dealing with numbers unless I absolutely have to. And also your exam is not going to have numbers on it, so might as well do everything parametrically. What we want to know is the linear acceleration of the ball over the distance AB. So then, before I go on, the slides themselves are posted. In terms of the annotated, that's something that I need to double check with Dida, because basically rules that I need to follow. I'll see if I can, though I may have to like almost redact some of the information if it's felt that there's too much information on some slides. So let me ask you this question. How would we figure out the linear acceleration of the ball over the distance AB? So I'm going to do the one where we look at what's happening to the ball as it is rolling. So what one could do is determine the initial velocity of 0, and then you're able to determine the acceleration at A. But that's going to get us the acceleration between O and A. What we want is the acceleration between A and B. So I see another question in chat. I'll hold off onto that until later on in the problem, since it will be something good to ask. So let me ask you this question. Over the distance and B, what forces are acting on the ball? We have gravity and we have force of kinetic friction. Why specifically kinetic friction? Because we are not purely rolling, because we are slipping. So this problem is over A and B is similar to something that was done in the textbook example 9-2. The difference is here we have slipping. In the textbook, it was not slipping. So if we're slipping, what we have is the acceleration of the center of mass is parallel to the slope. How would we calculate the acceleration? What would you recommend we do? So I see questions about net force, net torque. What I'm going to do is the net force. The reason why I'm going to do net force is because if I knew absolutely nothing about rolling, but I had seen chapter 5, that would be what I'd immediately think about. I'd try to basically do Newton's second law, since I know all of the forces acting on the ball. So we have X and Y. In the X direction, we have MACM with here, just so that I keep my directions consistent. So X, Y, basically positive, positive. So what is the right side of my equation equal to? we're looking at over the distance and b when it is slipping. So we have mg sine theta minus the kinetic force due to friction. How would I calculate my kinetic force due to friction? Right, this is where we'd want to know what is the normal force. We know that the kinetic force is equal to, basically we have mu mg cos theta. And then, well, I know what my friction force is. I know all of this. I can solve for this. And if you just solve for it, you get ACM is equal to the answer. So are there any questions about this before I go on? Why isn't the normal force on the free body diagram? Because I was so interested in the x direction that I just assumed normal force, and I forgot it. So thanks for catching that. Anything else that I can clarify?
So just to make sure, this is the free body diagram of the ball at point A, right?
It would be the free body diagram between point A and B. So basically, right here. It's where we are slipping. We are not yet purely rolling.
Okay, so I guess would the distance between O and A, would that make any difference then, or will that factor in later?
That will be relevant later.
Okay.
Yep.
Excuse me,
Yep.
Professor.
Yep.
What I don't understand is that because it's still not purely rolling, then the friction should like slow down the translational motion and increase the rotational motion.
Yes, it will.
Then
Yeah, so,
why
well,
is the acceleration
I should say,
towards...
maybe I should say it like this. What friction is going to be doing is we're still going to be falling down the slope, but we're not going to be falling down at a large enough rate. Basically, if there was no friction, we'd be falling down the slope at an acceleration of g sine theta. But with friction, we're still going to be going down the slope, but the acceleration that we're going down the slope will be less. So what friction is going to do is it'll slow down our acceleration. So we're no longer accelerating at g sine theta, but it's also going to be providing the torque necessary to start spinning the ball. So basically, at the end of the day, what's going to happen is we're still going to be accelerating downwards, but friction is going to spin the ball faster and faster. So then friction will eventually cause the ball to spin at just the right speed to reach purely rolling motion.
So what's happening is that friction is actually decreasing the acceleration, not the actual velocity of the ball.
Right. Yes. So the reason is because basically we're still falling downwards.
I see. Thank you.
You're welcome. Let me quickly make sure that I'm... Yep. Any other questions on this? Okay, I'm seeing no questions. What I want to do is go on to part B, where we're asked what is the angular acceleration of the ball over the distance AB. So how would we approach this problem? Torque is equal to I times alpha. Yes. Whenever you see angular or do anything with angles, immediately think about how can I incorporate torque into this? So torque is equal to moment of inertia times alpha. So what I'm going to do is draw my diagram again. We have Fk pointing like that. We have normal. Oh, I mean that would be right, just not as right as what I want. So we have Fk, we have normal, we have force downwards due to gravity. So then I see a question in chat. If you use torque in part A, can you just directly use it here? So when it comes to problems in physics, there are definitely going to be multiple different approaches. Sometimes you're able to do everything with torque. Sometimes you're able to do everything with forces. Sometimes you need to combine them, but you're still able to get the same answer. So regardless of which approach you use, you're going to, if it's a valid approach, you'll get full marks, assuming the question didn't explicitly say, solve this using torques or solve this using energies. I would say that even though there's multiple approaches, one approach may be more useful and quicker on one problem compared to another approach, but that doesn't mean that the approaches are wrong. It's sort of like when we do projectile motion, we can use kinematics to calculate the maximum speed of our ball. We can use kinematics to calculate the maximum height, or we could use energies and just note that the kinetic energy equals the potential energy. So then we know that the speed after we throw a ball upwards is just going to be the square root of 2gh. Will the ball reach pure rolling over the distance AB? Yes, so at point B, this is where we have pure rolling. Yes, pure rolling at point B. So let's talk about torques. How would I use torque? Like, what's going to be my net torque? How would I calculate everything? Torque is equal to Fk times our rotation at the contact point. Yes. So then whenever we see a torque problem, we could pick our pivot point being being the center of mass, or we could pick the pivot point being our momentary pivot. What I'm going to do is pick the pivot point for the center of mass. So I'm going to pick the pivot point right there. Well, we know this is a disk, so we know what the moment of inertia is going to be. So the moment, is it a disk? It's a ball, sorry, ball. Basically, we can look this up on the formula sheet. And we know that torque is going to be just Fk times the radius if I consider my center mass of my ball to be my pivot point. Why is it just kinetic force of friction times the radius? So I see we have gravity at the center of mass, so that means there's no torque. The distance between the frictional force and the center and the radial vector is going to be r, and we also know that the normal is going to be anti-parallel to the radial vector, meaning that the reason why I'm doing the torque about the center of mass is on the previous problem, I already calculated what my frictional force is going to be. So because I know what my frictional force has to be, I know that Fk times r is equal to I alpha, which means I know what alpha has to be equal to. And then we're done. With questions where the object is a ball, will we assume it's a solid sphere or it's a spherical shell? With a ball, you would assume a solid sphere. On the final exam, what we've done is we explicitly say what our shape is. So if we mean a ball, if we mean solid sphere, we'll say solid sphere. If we mean spherical shell, we'll say spherical shell. If we mean solid cylinder, we'll say solid cylinder. Is moment of inertia for a ball so for a ball, that's 2/5 mr squared, yes. Where, can I explain again why it's pure rolling? So over A and B, we have not reached pure rolling. At point B, that is where it's pure rolling. The reason why I know it's pure rolling is because that's what the problem told me. We know that eventually the ball is going to reach pure rolling, so then we just need to figure out. Yeah, we just labeled that point at which it reaches pure rolling, point B. Would we only use F static when the contact point is treated as a momentary pivot? Only use F static. So in this problem, we would not use F static because we are slipping down the hill. If we were purely rolling, so basically down here where we're purely rolling, this is where we would start applying F static. Over here, we would have the kinetic force of friction. Yeah, so purely rolling is when you use static. If you are not purely rolling, then you would use, depending on the situation, you would either use kinetic or you would use static. The different cases are on the slides that we did. I reposted the chapter 9 slides yesterday because there was a factor of R that was extra, but you would follow that notation. So then the final thing that I would say is kinetic force of friction is something that we found in part A. That's what you would find using Newton's second law. So now what I want to do is C and D together. It's because we want to know the angular speed when it starts pure rolling and how long it takes the ball to spin and slide before it starts pure rolling. The reason why I want to do these together is because the answers are really related. So when you see physics problems, when there's a multi-part question, that usually means like we're giving you the steps to solve the problem. But that doesn't mean that you have to solve one step and then the other step. You can solve two steps simultaneously if you end up with a series of linear equations. So how would I approach this problem? So I say find the initial velocity at point A and then apply kinematics. So let's do that. How would we find the velocity at point A? How would we find VA? So energy is one way. We could use the same way that we did for older inclined plane questions. I'm going to be using energy because energy oftentimes becomes quicker than doing kinematics. Is energy conserved over the distance d? Yes, it is. So change in energy equals 0. What's going to be my conservation of energy equation? So what I'm going to do is write that as height h, and then as people are saying in chat, we are able to know what h is from trigonometry. But then essentially we have half mba squared. Whoops, well, I don't know why I did a subscript there. We have half m of BA squared is equal to mgh, meaning we know what our velocity at point A is going to be. So let me ask you this question. I'm saying that energy is equal to half mv squared is equal to mgh. Why is it h? Like, I mean, there's an entire distance L right here, so why don't I need to take into account that distance? Since, I mean, we're going to be some distance here, this is going to be L minus h. Right, it's because we care about the change in energy. We're able to pick our reference point however we want. So then, essentially, this is where we calculate the change in energy of the problem. So essentially, what you could do is initially you could have mg L, and then you subtract mg L minus h, but then that just equals mgh. So this is going to give us speed VA. Now, what we want to know is the angular speed of the ball when it starts pure rolling and how long it takes the ball to slide before it begins purely rolling. So how would I approach that? What sort of formulas would I use? I heard angular kinematics earlier. Right, so we know that, we know that B roll is equal to omega roll times R. Yep. We know that velocity rolling is equal to my velocity at point A plus a t roll. I'll call this the center of mass for consistency. And we also know that omega roll equals initial velocity plus alpha t roll. Well, what do we know? We know VA. Here. We know VA, we know alpha, we know ACM. We also know R, and we know that we are initially not spinning. So that means we have 3 equations, 3 unknowns, and then that means that we can solve for omega roll, and we can solve for t roll. So this is what I mean when I say we can solve multiple parts of a problem simultaneously because they're all related. Reason why we know there's no spinning initially is because it's released from rest. So basically, if we have a ball released from rest, it's only going to slide down the hill without friction because there's no friction that's going to induce rolling. So there's no way that the ball would begin to roll. What else can I answer about this before we go on?
Professor, just to make sure, so what you did is that basically you split the whole thing into 2 parts, from 0 to A and then A and afterwards. Is that what you're doing?
Yes. Yeah.
And this is because at 0 to A we have energy not lost due to friction, and then if friction is introduced?
Yes. Yeah.
Okay, thank you.
Yeah. So you raise a good point about ultimately how do you know how to break up a problem? Let's say that The only question on this problem, and it would have been worth 15 marks, was part D. How long does it take the ball to spin and slide before purely rolling? And we didn't have any parts A, B, or C. The way to approach this sort of question is think about what's happening at each step of the problem. Think about it chronologically. I start the ball from rest. The ball is going to begin going down the hill. Does anything happen once the ball hits a certain point on the hill? And then once it keeps going down the hill, does something else happen when it reaches another point down the hill? So whenever you have new physics coming into the problem, that makes it a natural point to break up the problem. So basically, if I have this problem again, we have point O, point A, point B. I would say that this is almost like part 1 of the problem, part 2 of the problem, and then everything afterwards is going to be part 3 of the problem. So what I do is I break problems up chronologically. How would I compare the rolling problem on this one to the one on the final? Hold on, give me a second. Need to remember what the rolling problem is. Okay, I remember it now. I'll answer it like this. If I think that understanding this problem is understanding this problem is a good way to practice rolling motion, because there's multiple aspects of physics in the problem. We have something that's frictionless, we have no friction, we have sliding, then sliding and spinning, and then purely rolling. So basically, this problem is incorporating almost every single concept that we've talked about in the course. So then if you can do this problem and then you're also comfortable with what's in the lecture, I think that would set you up very nicely for the final exam. What is the final answer? Yeah, so the final answer, I didn't actually write down what the final answer is, because Dita had asked me only to go through the steps, but not actually provide all the nitty-gritty details. So, but what I would say is, if you have these 3 equations, then everything after that is going to be mathematics. And then you can double check if you solve these equations correctly by looking at the bowling ball problem and the motorbike problem, since those problems also have the same equations and those have solutions provided on the slides. So then if you can get those solutions on the slide, I think it's a good bet to say that you can you solve this problem correctly. Yeah, so are there any other questions before we go on? At 3, okay, and at point 3, will it still be accelerating during purely rolling? Yes, at point 3, we're assuming that the slope is still going to continue on. We're going to be accelerating while purely rolling. So our angular speed will increase, our linear speed will also increase. Point 3 is basically, it's similar to, I think, example 9-2. So will friction still exist when purely rolling? On a slope, yes. Basically, friction is what allows a ball to accelerate its rolling motion. Is it proper to solve D first then C? I mean, you can do either. I know that on final exams, on multi-part questions, I've solved, like, I come to part C and D. I've solved D first, get part C, and then I just say, well, here's my work for part D. Would you be expected? Yeah. So then would you be expected to know how long something is purely rolling for? Potentially. That would depend upon the specific circumstance of the problem. On this, we are not able to answer that because we don't know what's going on after it starts purely rolling. Does the slope go on forever, or does it eventually stop? So then, emphasizing this, in this problem, what we've done is, so for VA, we know omega naught, we know the acceleration of the center of mass, we know alpha. We don't know the rolling speed, the angular speed, or the time that it will take to roll. We have three equations, three unknowns. We're able to solve them simultaneously. Will the problem be conceptually harder or more mathematically difficult? I would say, my personal opinion would be, it's about the same. Like, if we go through a problem that's too easy, I would definitely say this problem would be too easy for the final exam. When we get to the more harder problems, then it becomes a little harder to say, is it easy? Is it too easy? Is it harder? So it's like right around the level. Can there be static friction when an object is purely rolling on a horizontal surface? In that case, static friction is going to be zero, assuming that the speed of the object is constant. So if we're not accelerating, static friction is zero. But we require static friction in order to start our purely rolling motion. If the ball is purely rolling, would friction have an effect on the linear motion of the center of mass? It would. Basically, gravity speeds up the center of mass, and then friction is what's going to speed up the rotation. Right. Once the ball starts to purely roll, what happens to friction? Does it decrease? When the ball starts to purely roll, friction will be maximized. Hold on. Actually, let me back up on that. I don't want to say maximized. Yeah, friction will decrease. Friction will decrease. There we go. Yeah. Since if friction was too high, then we'd start spinning too fast, and then eventually we'd get out of purely rolling motion. Can we use rotational kinematic equations during sliding? Yes, we can. Your kinematic equations will always hold true whenever you have kinematics. The equations make no requirement on what your object is actually doing. It could be purely rolling, it could be sliding. As long as you know what your accelerations are, something about your velocities, your times, your distances, how to relate all these, you're able to use kinematics. So then there's another question. When there's a slope, will there always be friction? Most times there will be friction. Don't want to say always, because I might be able to come up with some example where, given the forces in just the right place to make sure that we're able to purely roll, then there won't be friction. But in general, yes. In general, yes. Yeah, so in this problem, where we only have friction, gravity, and a normal force, there's always going to be friction present. Right. So is V equals omega r only purely rolling? Yes, that is the definition of purely rolling. So pure rolling, V Cm is equal to omega r. Is there any rotational acceleration until the ball gets to point A? There's going to be an angular acceleration. That's something that we solved on part B. Oh, sorry, you're looking at point A. Correct. There won't be any angular acceleration until we get to point A because there's no friction. And friction is what has to get us to start rolling. Anything else I can answer before going on?
Sorry, could you just go back to the previous slide? I just did something wrong. I wanted to see what I did wrong.
Yeah.
Oh, wait, sorry, not this one, though. One before
Okay.
this, over the very first one. Yeah, this one.
Yeah.
Thank you.
Yeah. So it's a question, is omega not equal to 0? Yes, it is. Yeah. So anything else on these slides? Because I know frictions, I'd say the hardest topic of the course, or if not, it would definitely, because I know rolling motion is one of the harder topics, that's why I want to make sure that we spend time on these rolling motion problems. So in summary, slipping means Fk or Fs depending on the situation. Pure rolling is always Fs. Constant pure rolling, no force due to static friction. I think that would be a good summary. Yeah, constant pure rolling, if we're not accelerating at all, then we don't have any static friction. Though the general way to do it is, if you're not sure, because friction's really annoying on these problems, it really depends upon the specific problem under consideration. The way that I do it is draw a free body diagram, include friction, and if there isn't any friction, then you'll solve that the friction force is going to equal 0. That's the surefire way to cover every case with and without friction, even the edge cases. Since it's the edge cases that I'm always worried about when I give qualitatively always or never answers. If the ball is rolling faster than its translational motion, is it kinetic friction or static friction? It's going to be, in this case, it would be, I guess it would slightly depend upon how the ball is initially rolling. So the reason why I say that is in the motorbike problem, what we did was we treated everything as static friction. So then in that case, it would be purely static friction. But if we had something like this where the ball was spinning, it had some sort of initial and translational velocity and it started spinning and it was spinning faster, but it was still sliding, then I would say it would be kinetic friction. So then the upshot is, if you're not sure if there's friction on the problem, include it in your torques, include it in your free body diagram, and solve for friction. It may turn out that friction is going to equal 0. So that's the way to approach any problem with friction. That will account for any case of friction that you have. The reason is because in Newton's second law doesn't really care what your situation is. It's a general statement relating forces, masses, accelerations, and torques, moments of inertias, and angular acceleration. Right, so what I want to do is go on to another thing that I was asked to do, and I won't be able to work, basically, I'll do the same thing that I did for the previous problem. I'll provide you with the tools, but I won't actually be able to write down, here's what the final answer is going to be. But what we have is a Christmas ornament. And we know that the Christmas ornament has 3 rods. It makes, yeah, it's basically in the shape of a snowflake. Ultimately, what we need to do is find the maximum angle that the snowflake will swing to when we throw a bunch of mass at the snowflake. So how would I approach this problem? So this is a 2-dimensional object. How would I approach this? What would be a natural way to break it up? So we see find the moment of inertia of a snowflake. What would happen after I find the moment of inertia? Okay, I see angular momentum, and then we would do energy. Yes. So this is what I mean when I say think about the problem chronologically. You have the snowflake, it's just sitting there, and then you throw a bunch of mass at it. So you think about what's happening to the snowflake before the mass hits it, what's happening to the snowflake after the mass hits it, and then the snowflake is going to move up at some angle. Then you'd want to try to calculate that angle. Now, as someone pointed out, you also need to work in center of mass in there. Center of mass will be something that, yeah, I guess we can think of it as a separate step. It's related to finding energies. So I'll group that in with the energy statement. So let's first so I'll write down my steps. First one, step, moment of inertia. Second step, angular momentum. Third step, energy conservation. Right, so then how would I calculate the moment of inertia of the rod? What I want is the moment of inertia about this point P. Right, so parallel axis theorem, yes. Let's see. There we go. Right, so how would I use the parallel axis theorem? I have 3 rods, and I need to apply the parallel axis theorem somehow. How would I do that? Right, so as was indicated in chat, someone wrote down the final answer. Yeah, seems about right. I didn't actually write down the final answer myself, just wrote down the steps, but that does seem like the moment of inertia. Though one of the properties of a moment of inertia is, whoops. Let's see, we get back there. One of the properties of a moment of inertia is moment of inertia of some object is equal to the sum of the individual moments of inertia. And then we know what the moment of inertia of each object is. We have 3 identical thin rods. So that means if they are identical, they have the same length, they have the same mass. And we also know from the formula sheet that the moment of inertia of a rod about its end is 1/3 ml squared. And then we also know moment of inertia of a rod about its center equals 1/12 ml squared. And then what we have is, so then what we need to do is to calculate the moment of inertia about point P. But as people already said, we can use the parallel axis theorem, since the parallel axis theorem says the moment of inertia is equal to the moment of inertia of the center of mass plus m times d squared, where d is the distance between the center of mass and the moment of and pivot. So whenever we have things that we need to calculate the center of mass for, we break up the object into its individual components, calculate the moment of inertia of each component relative to the pivot point, and then we need to add all the moments of inertia together. Are there any questions about this? Can we always assume the mass / child is a point mass? Yes, you can. Yeah, in this case, we can assume point mass. So Play-Doh is point mass. Basically, if it doesn't say the radius of the object when it says like small ball of mass m and it just doesn't provide you with the radius, you can treat it as a point mass. Right. So then, is the snowflake center of mass located at L/2 without considering the ball? Yes, it is. What else can I answer before we go on to the next part of the problem? Okay, I'm seeing no questions about moments of inertia. So now I want to talk about angular momentum and how we deal with the point mass. So from part A, what we calculated was the moment of inertia of the ornament. Sorry, I shouldn't say part A, I should say step 1. Step 1, moment of inertia of the ornament. And then for step 2, well, I'll talk about that after I answer the question in chat, since I guess many will be wondering it. On these sorts of questions, we're not going to give you some really weird shape. We're going to be giving you a series of shapes. So like this, we give you something where you don't know the moment of inertia of the entire shape, but you can calculate it because we've told you what the shape is made out of. So then on this question, make sure to use your formula sheet. So then for part 2, what we need to do is conservation of momentum. Conservation of angular momentum. And then what would my initial momentum be? What is my initial momentum going to be? Right. It'll be whenever we have an object that's colliding with another object and we need to worry about angular momentum, we need to specify what is our pivot point going to be. And in this case, we know that the angular momentum is equal to the radius cross the linear momentum plus the initial angular momentum of the ornament. But this thing is just equal to 0 because the ornament is not static. It's not doing anything. And then here, r is the distance from pivot. And then p is the momentum. So as a general rule, we have two formulas for angular momentum. We have L equals R cross P, and we have L equals I omega. When would I use which formula? Right, so think about it like this. Is the, which one describes a point particle? Which formula describes an extended object? Right, so then this one is whenever you have a point particle. And then this one is whenever you have some sort of extended object. So, i.e., not point particle. Where this distance is going to be your radial vector. Once the object, yeah, that's going to be your radial vector. So then, this is where I want to talk about how do you actually calculate R cross P. So what's the magnitude of my initial angular momentum? What's the magnitude? Initial angular momentum. Right, so we have basically RP sine of, I'll call this phi, where this is the angle between R and P. So then if I draw a diagram, so we have, this is going to be my P vector, this is going to be my R vector. Let's make sure I draw it correctly. Now, draw it like that. I don't like obtuse angles. We'll draw it R there. Then we have P there. This thing is angle phi. And then what we're able to do is use trigonometry. Use trigonometry to relate theta and phi. So what I mean by this is essentially start drawing right triangles. Since if we have a right triangle, we know this angle. So we know this angle, meaning we know this angle, meaning we know this angle. Any questions about this before we go on? does the radial vector always point to the center? So the radial vector is always going to be from your pivot to your object. Or, sorry, from your pivot point to your momentum. So whenever you calculate angles, and you don't know an angle, start drawing right triangles. Use trigonometry. Since if you use right triangles, you already know that one of the angles has to be 90 degrees. If you know the second angle, you automatically know the third angle in the triangle, which often gives you additional angles in the problem. So then you're able to calculate what your angle, what the angle you care about, what it's going to be. So then in this case, what we end up getting is, let me quickly double check something. Aha, yeah, there we go. So then what we get is phi is equal to pi over 2 minus theta. So then basically you get that sine of phi equals cosine of theta. I always need to quickly double check when I'm using pi's and pi over 2's in my trig functions, just in case I get a minus sign. I knew it at one point off the back of my head, on top of my head. Now I need to quickly make sure that minus signs I don't forget a minus sign anywhere. So then ultimately, what we care about is this angle phi right here. Since that's going to be the angle that we care about between the radial vector and the momentum vector. So one way to think about it is this angle is theta. So this is going to be 90 minus theta. And then this thing is going to be see, pi over 2 plus theta. Pi. Yes. Yeah, so basically start drawing right triangles and note that the sum of the angles in a right triangle is equal to 90 degrees, and the angle from a straight line, basically this angle, is 180 degrees. So that's the way that I approach these questions, because there are definitely, you can use the cosine law, sine law if you don't have right triangles, but at least me personally, I like drawing right triangles since that's what I'm just most comfortable with. And then I use opposite angles, supplementary angles, complementary angles. All of those buzzwords that I never thought I'd really need to worry about when I was first learning it. So the second last thing I want to mention on this slide is know where is your angle is located. Here, theta is specifically this angle. So we have the initial angular momentum. What is the final angular momentum going to be? What's the expression for the final angular momentum? So does the moment of inertia change after the collision? Yes, it will. So in this case, after the collision, we know that the moment of inertia is equal to the moment of inertia of the ornament plus moment of inertia of the point mass. And then we know that the initial angular momentum equals the final angular momentum. We know an expression for our initial angular momentum. We know our final angular momentum is equal to our total moment of inertia times omega, and we're able to solve for omega. are there other questions? I noticed that there were questions in chat, and I feel like I might have missed some questions since some of them were being asked and answered simultaneously. So if your question wasn't answered, please highlight it in chat again. Right. So then the questions seem to come down to the point mass and moment of inertia. Moment of inertia of a point mass is just mr squared, where r is the distance to the pivot point, So this is basically distance of radial vector. And you will either be given this or you'll need to quickly solve for it, depending on what the problem says. So in terms of the parallel axis theorem, essentially the point mass is a very, very special case of the parallel axis theorem, because a point mass is a zero-dimensional object. It doesn't have a center of mass, because to have a center of mass, it needs to have some sort of extent in at least one dimension. So essentially, the point mass is the parallel axis theorem when the center of mass moment of inertia is equal to 0. Right, so then what we've done is find the angular velocity right after the collision. And then the way that we found the angular velocity was basically by doing geometry. We draw a right triangle, we identify what our angle theta is, and then we keep calculating various angles until we find the angle between our radial vector and our momentum vector. And the momentum is going to be conserved in this because there's no external torque acting on it. And even though it's an inelastic collision, momentum is always going to be conserved. So what I want to do now is part 3 of the problem, where part 3 of the problem says energy conservation. What's my initial energy? So this is right after the collision. So initial energy is right after collision. Oh. I was going to enable that just in case. Final energy is going to equal essentially at max height. There we go. So initial angular momentum, as people said, is just half I omega squared. There's only a rotational part to the kinetic energy. So right after the collision, so it'll be half I omega squared. Well, we know this. We calculated the moment of inertia, we calculated the angular velocity. What is the final energy? Right, so then the final energy is mg delta h. Is there no translational kinetic energy because it's right at the start? Yeah, basically, the center mass of the system is rotating in a circle. It's not actually moving towards the left or right. So then that's why we don't use translational kinetic energy. So let me ask you this question. How would I calculate delta H? Right, so then I see that the answer has basically been written in chat so far. So let's break it up into steps, where first we need to worry about center of mass. Originally, we have the center of mass of the object is located right in the center. Then the Play-Doh hits, and then the center of mass is going to move where? How is the center of mass going to change? It's going to move down some bit. So let me ask you this question. Why do we care about the center of mass? How is that going to help us? How does center of mass relate to potential energy? Right, it's where gravity is acting. So if I draw a diagram, and here I'll just draw a diagram of a general system. We have some system. So this is the location of my center of mass. Here's my pivot point. Then afterwards, the object has rotated. The center of mass is in the same location, but there's now a height difference, meaning that that height difference gives rise to gravitational potential energy. Is everyone happy with that so far? Doesn't the ballistic pendulum move in the same way as the pendant? So why do we need to consider translational kinetic energy instead of rotational kinetic energy for ballistic pendulum? Good question. So translational kinetic energy and rotational kinetic energy are definitely connected. But with the ballistic pendulum, if I draw the pendulum over here, the bullet ended up right here, meaning that the center of mass now moves somewhere towards the left. Whereas in this problem that we're doing, the center of mass moves straight down. The key is center of mass is still along the same axis as my radial vector. Whereas in the ballistic pendulum, the center of mass is no longer along the axis of the radial vector. So that's why for the ballistic pendulum, it's easier to use linear momentum, translational energy, whereas for the pendulum in this problem, the object in this problem, we use rotational kinetic energy and rotational angular moment. Any other questions before we go on? So what is the center of mass? So for the center of mass, we have this formula. So do I want to write it in 1 dimension or 3 dimensions? We'll write it in 1 dimension because we're only considering the center of mass moving down. So in 1 dimension, the center of mass of some object is equal to m1 x1 plus m2 x2 plus dot 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 plus mn xn divided by m1 plus m2 plus so on. So each of these, so x1, x2, xn are locations of each constituent object's center of mass. So what I mean by this is the center of mass formula is right here. And x1, x2, all, as many x's as you want, are going to be the location of each individual object center of mass, making up your entire center of mass. So what I mean by this is if I have, I'll draw, there we go. Here's some system where the center of mass for this is x1, x2, x3, x4. What I can do is plug my center of mass equations into this expression, and essentially what I get is going to be the center of mass for the entire object. So then for this particular problem, all we need to know is where's our original center of mass located and where is our point mass located in order to calculate the new center of mass. So does that answer that question? So then I'll just say that if we have two objects, then the center of mass of two objects is just going to be m1x1 plus m2x2 divided by m1 plus m2. For three objects, or 2 or 3 dimensional objects, center of mass is a vector. So that's equal to m1 r1 plus mn rn divided by m1 plus dot dot mn. And then x1, x2, x3 are the center of mass of each object, where sorry, this means one dimension.
Sorry, Professor, when you say the center of mass of each object, for example, for the small point mass that is being shot at the start, where would we consider x2 to be?
So this would, I'll just write down x1. x2 would be wherever the point mass is located.
So from the pivot to the place it's located at.
Yep.
Thank you.
You're welcome.
Oh, sorry, just want to make sure. So it all based on our reference point, right? So if I don't pick P as my reference point, then even though my center of mass is at the same location, but X will change.
Correct, yes.
But we pick P here, so X it's just like L over 2 and 4L over whatever, blah, blah.
Yeah. I think it gave us, in the problem, it told us where point A is located. Yeah.
Oh, okay.
In the problem, it said, yeah, it told us the distance PA.
Okay. And also, sorry, just one quick question.
Go ahead.
The questions asked like saying, oh, there is friction, but the question didn't say anything about the friction. The question just say, okay, there's the friction, but it didn't tell us about the coefficient or anything. Can we assume we know the friction, or we can't assume that?
Yeah. Frictionless axes.
Oh, I mean, like more generally. Like,
Oh, more general. Oh, that would be annoying to deal with. In that case, we would have to give you something about friction, but
okay.
we'll stick with frictionless.
Okay, but we just don't assume, like if you say there is friction, we don't assume we know the magnitude of friction already.
Right. If there's friction in the problem, we'll explicitly say friction.
Okay.
Yeah.
Sure.
Yeah. Or well, I should say if we'll usually say friction in the problem. In other cases, like if we have some sort of disk rolling on the ground, then we might not explicitly use the word friction, but then that would be a purposeful reason, because we'd be assuming that you would recognize there has to be friction in order to do whatever we're wanting with the rolling motion. But in places like this, where it's not immediately clear whether there would be friction or not, you'll explicitly say frictionless.
Okay, so in the final, will we have something like given variables and value? Like, will we have this line, or you guys just don't give it to us?
We will I don't want to answer that question, but
Okay.
or more specifically, I don't want to answer it directly. But what I would say is the wording that we've chosen is familiar to you. So then you would have already seen the specific wording before, or at least the specific implication behind the wording.
Okay. Thank you very much.
You're welcome. Right. So since I do want to have a break shortly after this, the one thing I'll say is, you know, the distance of the center of mass. We know that this angle is going to be phi, meaning that from trigonometry, we know what this quantity needs to be. It's the same procedure that we used to solve the general object in one of your moment of inertia problems in chapter 8. Right. So basically you can get H will then give you what your angle is equal to. Since what you have, if I draw it again, XCM, XCM, H, and phi. And then you can use trigonometry to determine phi. Right, so then will we have a separate statement to tell us which variables we can have in our parametric equation? Yes, we explicitly have this is what you're given. So then for the length, what we care about is the new center of mass. Point A allows us to calculate where the new center of mass is going to be located. And then you can determine, ultimately you determine by doing conservation of energy, and then you're done. Anything else that I can answer before we have a break? So then I would say before talking about the break, the way that we get the new center of mass is basically by using this equation. We use our center of mass equation. So then in terms of how long the break is, I will show you what questions we're considering afterwards, and then we'll talk about the break. This one, we're just considering the same question that was on the quiz. It just happened to be question 2 of the 2020 exam. Then we're going to be considering this question, a rolling motion question. And then I have extra questions that we can do if we have time. And then the 3 questions that I really want to get to are 2020 questions 2, 3, and 4. So then this session is going to last until, I'll be here until 6:30 p.m. or in practice until I answer all questions. So then for breaks, because we've already been talking for 2 hours and 12 minutes, how long do people want as a break? I'm optimistic that we're able to get through the rest of these questions before 6:30 p.m. So, right, so I see 4 different answers, all of them increasing. I also appreciate the dad jokes in there. Right, so then it seems that let's do $15 to 20 minutes seems to be the common thing. So let's do 4:35. This will give you a time to get something to eat or do whatever you want, stretch your legs. And then So then regarding that, there was someone who wanted to go through the quiz question, so I'm uncomfortable skipping the question. I won't go through all the details. I'll just reiterate it again. So it won't take the same level of time as the previous question. So then let's do 435, and then I'll say what the general procedure is going to be. Okay, so see you all at 435. All right, let's. Okay, it's 4:35. Let's get started again, where what I'm going to do is quickly go over question 2, since that's the order that I said we'd go over the question in, and then we'll move on to question 3. So whenever you see a equilibrium problem, how would you approach it? Free body diagram and torque. So equilibrium, and there. Draw your free body diagrams. And then in an equilibrium problem, you also know that the sum of the forces are equal to 0 and the sum of the torques are equal to 0. So once you have your free body diagram, you basically just apply Newton's second law and then you would be done. Well, you would get your basic equations, then you can solve them for whatever you need to know. So let me ask you this question. What sort of forces are in this diagram? All right, we've got gravity. Oh, I need different. Gravity, we've got tension. So we've got Fg, we've got Mg. And then the important thing is whenever you have hinges, you need to have a hinge force present. And then that will get you your, you can apply Newton's second law in the x and y directions. So you would be getting sum of the forces in the x direction is equal to 0. Sum of the forces in the y direction is equal to 0. For torque, how would we approach that problem? Right, pick the best pivot, pick the best point with the most forces acting on it. Basically, in this case, we can pick the hinge as our pivot point. Whenever we have a pivot point, it can be a real pivot or a virtual pivot. Yeah, so then there's a question, will you be told if the system is in equilibrium? Well, I remember the question that's on it. Here. Before answering that, I want to remind myself of the specific wording of the problem. The problem will be evident that it's in equilibrium. Yeah. Yeah, so if it doesn't say anything about some sort of rotational acceleration or translational acceleration, then it would be a good bet to assume that we're in equilibrium if it does seem like an equilibrium problem. In this specific question, I'm not sure. So this came from 2020. I don't know whether there were a bunch of questions on the equilibrium problem or if like the final exam had something like question 2 is an equilibrium problem or something like that. Yeah. So then there's another question. Can we always break the hinge force into vertical and horizontal components? Yes, we can. In general, hinge forces are going to have a vertical and horizontal component. And then in order to say the direction and the magnitude of each component, this is where you need to solve the problem. So are there any questions on this one before I go to the spring one? When we guess our hinge forces, how do you know if your guess was incorrect from just variables? So short answer is it really depends on the specific problem. If we get like, for example, if we get the hinge force equals negative mg, well, that means that you guessed the hinge force in the wrong direction. If you get something like hinge force is equal to mg L over L minus mg LB over L plus mg LC over L, then it really depends upon the specific lengths within the problem. And then if you don't know anything about the lengths, then you wouldn't necessarily know whether your hinge force was pointing in the right direction or not. But that's okay, since ultimately what we care about is at the end of the day, the magnitude of our hinge force. Or if you get like a hinge force equal to negative mg, you can leave it at that. Anything else that I can clarify before we go on? On the exam, are we given the direction the hinge forces or if the pulleys are massive or massless? Yes, for the pulleys, we explicitly say massive or massless. And then for the hinge forces, this is where you need to guess them. But then it's regardless of what direction you guess, as long as the math that you carry through is correct, you would get full marks on it, because the only difference is your overall answer will be off by a minus sign, indicating that the hinge force points down instead of up. Anything else? In the multiple choice question, do we need to know the exact direction? Yeah, so then for the multiple choice question, I can't answer that at the moment, but, or at least I don't remember what the multiple choice question is, but we've made it so that it is doable without having to worry about direction. What would the question on the exam be similar to this one's difficult? Hard to say. I would say that in general, the equilibrium problems tend to be conceptually easier than the other problems, because everything comes down to sum of forces equals 0, sum of torques equal to 0. Impose that and go. Yeah. So then, is trig going to be this difficult? Hold on. I'm thinking through other questions on the exam. I don't think the trigonometry should be overly difficult. Yeah, so one of the downsides is, well, trig is extremely related to physics, because everything comes down to lengths and angles, changes in lengths, changes in angles, basically time derivatives. Lengths can refer to positions, angles refer to angular quantities we can differentiate with respect to time to get velocities. So I'd say that the trigonometry is doable. I'd say that it's not going to be the main part of the problem. But for everyone here, if you do have questions about trigonometry, like please ask them in my office hours tomorrow, and I'll be more than happy to go through any trigonometry problem with you. So then, did it imply that the moment of inertia problem is the hardest problem? Is it because there's a horrible shape, or because moment of inertia is more difficult? So I'll answer it like this. I would say that it's because moment of inertia is more difficult, because when I was doing physics in first year, I remember understanding energies, kinematics, forces, the things that tripped me up: moment of inertia and rolling motion. So then, what is my office hour link? It's posted on Learn. It is the same one that's for Thursday office hours, but I still use it Tuesdays and Fridays. Right. Thank you for posting that. Yeah, so then, so in the quiz, so this came from the quiz question: how would you know if you guessed the directions correctly? In the specific quiz question, I don't believe you could, because, well, could you? If the diagram was drawn to scale, you'd be able to relate the distance between A and C and D. But there are things like the polar bear question, where ultimately, based upon the parameters you know nothing about the direction of various quantities, just because there aren't any numbers. Yeah. So then, on the quiz, is it safe to assume the diagram is to scale? Yeah, I'd say that's a safe assumption. And then, do I think the final exam is harder than the midterm? I would say, yeah, so I would say, answer it like this: harder in the sense that there's more topics present. We're in the harder part of the course, but it's easier in the sense that the long problems that we're giving you will relate to the harder aspects of the course. The problems on the multiple choice will relate to everything. So then, let's say that you don't know kinematics, or you just blank on kinematics. That's going to be a multiple choice question or two. If you get that wrong, it's bad, but it's not horrendous compared to getting a long answer question wrong. So I know that I really hummed and hawed about, is it harder than the midterm, easier than the midterm? I would say in some ways it'll be easier, in other ways it'll be harder, just because how the various topics are related. We're in the harder part of the course, but then if you don't know kinematics, it's bad, but it's not going to tank your mark. On the exam, will there be cases where the direction has to be assumed? No, there won't be. I have double checked that, and basically tonight and tomorrow is when I'm going to triple and quadruple check that. Yeah, so what I'm working on is making sure that, verifying that the question has all the information available. And if there's a reason why we don't give a specific piece of information, it's because that's what the question is all about. Right, so what I want to do is go on to question 3. Where's question? There's question 3. Will forces and acceleration variables be magnitude unless otherwise specified? it's going to be evident on the exam whether something is a magnitude or whether something also has direction. Unfortunately, I can't go into more detail than that. Yeah. So then let's approach this question. How would we deal with it? How would we find the period of simple harmonic oscillation? Or what would be the first thing you'd do? Free body diagram and a net force. So free body diagram sounds like a good idea. So let's start doing that. I'm just pulling up what Dita did, so I make sure I provide the same level of detail on this problem. So let's look at free body diagrams. What forces are present? Right, so there's tension K1, X1, K2, X2, mg. How many tensions are present? 4 tensions, but they're all related. So let me draw the diagram. We have mg downwards, we have T4 points that way, we have T4 here, we have T3, we have T2, we have T1, T1, and there we go. And then I've run out of space. So then let me consider the connection points between them. So we have, let me write this as point A, point B. Why do I feel like I'm missing one? Nope, I got all my connection points. And then point C. So then let's focus on connection point A. Connection point A, connection point B, connection point C. What forces are acting at connection point A?